So truck scales and what we want to do. Picture this shows two different size adapters. And will there be a difference in the measured value? When I say two different size adapters, we're looking at this an intercom scale. Really manufacturer of a lot of the scales, aircraft, truck scales. And all we're doing is comparing two adapters. So knowing that this is the specification on this scale is plus or minus 200 pounds. Well, it's actually 1% of applied, but so it varies from 2,000 to 20,000, from 20 pounds to 200 pounds. And what we observed with the different footprints here is difference in readings. And those readings were still within the tolerance, though what you have to worry about is when we have a tolerance plus or minus 200, what if I was closer to one of those tolerances? Would I call it out when it's actually in by using a different rubber footprint or not? The difference between those two was about 70% of the tolerance. Like I said, 140-pound difference, that's over here. So that eats up a large portion of the tolerance and does make a difference. And this is a better zoom in of that, the tolerance, the difference in pounds. And you can see not much difference at the low forces. And as you got to the high forces, it was about 70%. This one's like just a standard scale. I don't remember the manufacturer name on different size plates. One plate, the larger plate on this cell, the readings you can tell were pretty darn good at 40,000 and 10 pounds the whole way through. The small, is it linear? No, the way this is gauged is probably not that linear. Though if I used a small pad on it, the difference was significant, 470 pounds at capacity and a 1.3% overall difference. If the tolerance is 1%, I'm not within the tolerance if I've switched my pads. So this is not a good scenario to be in as far as that goes. What you want to do if you're doing any truck or aircraft scale is you want to look at the product manual, and hopefully the manufacturer has guidance, recommended guidance of what size the adapter should be. And the adapter that's used during calibration should be composed of the same type of rubber and should have really the same footprint of the tire. Different adapters are going to have different footprints, and this next picture here I'm going to show you like what best replicates the tire is probably oval. And we have a 9-inch round pad, that's this one right here. We have an 8x8 pad, that's this one right here, and then we have a 10x10 pad. Manufacturer intercom, they're very good on their manual to call out what size should be used in it's towards the back of the manual. So if you don't do it though, and you look at these different scales, and we had a whole pile of them come in, so we got to test a bunch of them, but the 10x10, dramatically different results than the rest. And I don't know why this does that with this this little arrow, but dramatically different results than using the 8x8 or the 9-inch. And if I use the 8x8 and 9-inch round, the difference wasn't very significant. A resolution count, I think maybe 30 pounds is the worst case scenario on a scale that's spec to the 1% of reading. So, but if I used the 10x10 pad, it was really bad. Its difference is for every point but the first one, it would be all, we would say would be all be out of tolerance. So just important to look at that, make sure, and this is that bigger scale. And what seems to be the difference in this one is the rubber bending over the edge. for this PT300. I know the aircraft scales, the 60K and the other ones, you need to use the right. It will put you out of tolerance because they're spec'd at 0.1% instead of 1%. So just make a mental note if you're doing aircraft scales, look at the manufacturer's manual, replicate that, replicate via the recommended adapters that the manufacturer provides. Importance, best practice for other adapters, wrapping this section up on the adapters, is to send top blocks or plates with the load cell being calibrated. Each load cell should have top blocks and they should be ground flat. Using tension adapters with steep spherical radius will provide better vertical line of force, producing better results. ISO 376 appendix, highly recommend looking at that on the load cell side. And on the scale side, look at the manufacturer's spec sheet, not spec sheet, look at their manual, and near there, it'll tell you the footprint of the adapter, and it should be composed of rubber. So we've covered load cells. Hopefully you have a better understanding of, like, if I want to reference load cell, or if I have techs or field service and I'm looking at all these, now I have so many choices that you may be able to narrow it down. Multi-columns if you want portability, lightweight, really, really good accuracy, versus shear webs if you want good reference standards. If you want to go for the full gusto, you could buy an HBM DMP 41 meter that I didn't talk about. As far as indicators, it's $70,000, and you could buy GTM GmbH cells that are about twice as good as the Morehouse reference cell, but then they're about 5 times the cost too. So if you want a very, very good cell, it's going to be the Morehouse shear web, ultra precision shear web, and one of these meters. And then you have to decide on what do you want meter wise. Like, can I live with a computer? Does the indicator have to be better than 005? That's a nonlinearity specification. I don't care too much about nonlinearity specifications. To some extent, you need to decide, how easy do I want to make things for myself and for my technicians? How close do I want to be to nominal values? Do you want portability? Like, if I'm doing testing machines, because not everybody's doing E74, so about 31% of the people here are probably in that market where, hey, this portability of this, I can use coefficients, which we'll talk about. If I use a computer, now I can capture the readings by hitting spacebar or something else, dump them into a sheet, kind of automate as much as I can the calibration of a testing machine. That might be appealing. If you just want something that's going to check a press or something, maybe like I could get one of these handheld units that someone can program close to direct reading. There's stuff about TEDs. This PSD meter will read TED chips, which I'll talk about. It uses batteries, so you don't have to have a plug-in source. I can just pull the load cell out, check something really quick, and go. The price you're going to pay is more bias, less accuracy, but it depends what you're calibrating and what you have to do. And then it comes down to, do I want an actual display? Do I want a low coefficients? Do I want, something beside the machine that has a reference? So you start going over these, and how do I pick what I need, right? You're going to choose based on how good you need it to be, right? That's accuracy and uncertainty. Wired or wireless? Do I want extreme portability? And we have systems for all of that. Environmental conditions. Is it harsh? Like, are things going to really get beat up? Am I going to go into an environment that I don't feel safe taking a laptop in with me? I actually had somebody say that in some of their environments. So that's a factor. 4-wire, 6-wire sensing. We haven't talked about that yet, but it's something that I would always lean 6-wire if I had the ability to do that, because cable length makes a difference. Ability to use coefficients. Like, what the heck does that mean? I'll show you. Price, obviously that's going to rule some part of my decision, ruggedness, and then number of load cells. And then is TEDS something you want or need? Do you want the pain in the butt? I'm biased against TEDS, and I say that coming into this. And the reason I'm biased against TEDS, this technology was invented around the 2000. It's an IEEE standard. And then it's all this industry 4.0, and they have these buzzwords and terms. Create smart, interconnected manufacturing systems that leverage automation, real-time data, artificial intelligence to optimize efficiency, flexibility, and decision making. And what happens is some salesman somewhere sells somebody a load cell with these TEDS chips, and it sounds like the greatest thing in the world. And what ends up happening is the accreditation body or the person that comes for your site, if you're accredited, they come in and they determine that you're breaking all of these rules on metrological traceability that require the undocumented chain of calibrations, each contribute to measurement uncertainty. And when I say you're breaking the rules, I mean, they buy indicators and they never calibrate the indicators. The assumption is my indicators are perfect. I hook the TEDS chip up, I put it in the load cell, indicator reads it's always reading what it should read. No, what needs to happen is that indicator needs to be calibrated with the load cell or separately with its own chain of traceable measurements and uncertainty analysis. So that in itself makes TEDS a bit of a pain in the butt. As people tend to think it will calibrate are confused, and TEDS will calibrate the load cell, but yet it doesn't do anything. It's just a little EEPROM chip. It's your USB, for lack of a better, it's a little more complicated than that, but for lack of better understanding, it's a USB that has some memory on it that someone programs in a lab, and then the meter reads typically these two span points and spits out and converts that digital signal into a numeric pounds force, kilonewtons, newtons, kilograms force, whatever you're reading. That's all it does. And the end users often purchase load cells with TEDS expecting this full calibration functionality, but they receive incomplete or incompliant systems. It doesn't say TEDS might not be good for you. It's just saying understand the basics. And TEDs have all of these templates, right? And there's template 33 for millivolt per volt. 31 is for milliamps if somebody's working in current. Template 30 is for voltage. You can set like 0 to 10. There's some linearization templates in there. Template 40 provides linearization piecewise, and we have a graph with that, different options. And template 41 allows us to use curve fit and polynomial like regression analysis. So what does all this mean? This is already starting to become, and even I've taught this to in-house, I've taught it to other people, I've written papers on it, and it's, to me, it's already confusing in the word salad that it is to try to explain this. So the best I could do is come up and say, okay, this template we're overloaded with template. This template 33 is what we want to remember for right now. Most meters that say TEDS will be TEDS compliant with template 33, which means you can store information on the load cell, such as the serial number, the capacity, and you can store a 2-point span. What that means is if I have a 10,000 or a 25,000 whatever load cell, 25,000 Newton load cell, could be pounds force, could be whatever. That means that I can pick two of these points. I do a calibration and I can pick two of the points where my force applied and my millivolt values, and I span them in. So what I've done here on the right is what you're seeing is basically saying my span points were 2%, which was 500 pounds, which is not on this curve right here, and capacity. My span points were 2,500 and capacity. My span points were 0, and 80%, so 20,000. My span points were 0 and 100%. Now, people that have span load cells know the games you play for customers or for yourself internally, which is like, let me pick, and some of the load cell, some of the indicator language is such that typically says, hey, we tend to find that 0 and 80%. Anyway, back to our specifications, nonlinearity. I'm trying to span this load cell at 2 points, and I'm trying, my load cell specification sheet said my nonlinearity is better than O2. So if I hook this up to TEDS and do these points, should it be better? Should it not be better than O2? Well, this is one of those O2 load cells. And if we look at all the points, our best series seem to be this 10% in capacity, which we generally O2, but 2500 we didn't get in there. So something's going on mathematically, which in this cell, I mean, an S-beam could be different because it could have more linear behavior. I want to forward with that. Though something's going on here, we have quite large errors at the bottom end, no matter what we span in. And one goes positive, one went positive two at 2500, and the other went negative. And you can see how these errors went. And then they all typically come together at capacity. When I span at 0 and 100%, my capacity number, so at 25,000, when this reads 0 over here, that means my indicator reads 25,000. These numbers are the percentage off from nominal force. So this might help when I talk about that. So that means my force applied is something, and my measured value may be off. That's what I call a bias, offset, systemic measurement error. All these terms, the vocabulary international metrology defines some of them. I like to say it's just a bias, right? We know if it's repeatable, it's a bias, and the bias should be corrected for. A lot of people do not do that, but that's another story. So what we end up knowing is that if we apply 10,000 and our indicator reads 10,009, we say, okay, let me do it again. We apply 10,000, indicator reads 10,009. Guess what? We apply it again and it reads 10,009. I have a bias. So the right thing to do with this bias is correct for it. And correcting for it means that the technician, to generate 10,000, loads the device till it reads 10,009, thus defeating the whole purpose of TEDS in these span points, because the only point I got was when I did 0 and 100% was at 25,000 when I did the 2-point span. So if we look at this, and this is just simple conformity assessment, I'm taking the measurement uncertainty into account. When we look at this and we do not correct for that bias, and all of a sudden I say, I have this device, Morehouse sold it to me, the nonlinearity spec is O2, I paid them for calibration, my data shows O2, I program these two of the points that I randomly pick into my meter, we're at 10,000, I have this offset of 9, and then I go use this device to calibrate something else that they say is good to 0.1%. That's my specification here, 10,000, which is plus or minus 0.1 of 10,000, which means my lower specification limit is 9,990, and my upper specification limit is 10,010, so plus or minus 10. And I do not correct. I just program that, and I was off my measured value. I report then to the customer that when I applied 10,000 uncorrected, my measured value was 9987, which is outside of the specification, and then I proceed to adjust the instrument. Now, harder to follow, bit of word salad, which basically means I'm thinking 10,000 is actually 10,000. I programmed these span points. I have the bias. I did not adjust for the bias one bit. And now I'm in this scenario where I'm calling something bad that when I look at it, the risk, the PFA that I've calculated here, and not to get into specific and global risk, but this is a specific risk model. I've calculated this at 87.67%. I call the device bad. I proceed to adjust this device when I shouldn't have. If Morehouse or whoever programmed the TEDS chip and then did all these numbers for me and told me that I needed to load the device to 10,009 to apply 10,000, and I actually do that. I don't rely on that 2-point span being good. I actually have quantify, measure it, and know that I need to apply 10,009 to get to 10,000. Now I do that with the exact same instrument, plus or minus 10 pounds. My measured value, all we did was shift it 9 counts. That's all we're doing here. And my risk is to the customer, PFA is 1 point, that's probability of false accept. That says calling something good when it's bad is well under the 87. It's 1%. Now I'm not adjusting the customer's instrument. I'm saying your instrument is good. I'm meeting this guideline, and the guideline that I'm looking at, we were 4-1 on the TAR side, which actually equated to a different number. But so I'm 4-1 TAR side. I'm saying this instrument's good. It actually is good. I send it to the customer. So I have a scenario where I'm adjusting versus not adjusting. And then if I keep doing this along the way, and every customer does this along the way, what happens? Like if we keep correcting our bias and not using that span and actually loading to the right points, and this convoluted Excel file that randomly generated uncertainties, and that's where you're getting this from. I get to the point where, yeah, I keep calling things out. And then somebody else, they're not as good. Somebody else does this and somebody else does this. Guess what? These are all out. So looking at general TEDS in that 2-point template 33, if we look at some of the higher end TED systems that do more than just this template 33, or are more than TEDS enabled, which does absolutely nothing. Don't waste your time on that. TEDS enabled means nothing. It's some gimmick to sell stuff. It has to be actual TEDS that's the IEEE compliant. So if we look at the higher end templates, which most meters do not do, template 40 and template 41, template 40 allows us to span up to 127 points. So we can really drill down, get all of those 10 data points I showed you. We can drill that down. We can do a lot with that. Template 41 allows for polynomial equation to be used. Look at this, and we graph it. Now I've added lines to our graph. I've added lines for, okay, we're not even going to do a 10-point span. We're going to do a 4-point span, use that template 40. And we're going to compare that against some polynomial curves down here, green, blue, and brown. And those polynomials in Excel function, line S function, is a linear regression. And so you're curve fitting all the data set and you're generating a formula that helps you predict the curve. And if we look at this, just this simple thing right here, template 33, I had a max error of 0.1. Right. My example was that, hey, if we get that about 9, which my example had 0.09 in it, but template 40, four span points, I can reduce that bias error to 0.3. If I use template 41 and use coefficients, I can reduce that error to 0.068%. So I don't care like what everybody wants to do with things and how I just want to show you that these other templates, the point of it is true TEDs, if you're looking at it, template 40 and 41 are going to be much better. And we could hone in on this 0.03% and make it much better. So ideally, some of your problems with TEDs, which we started talking about bias and everything, is these templates, 33 or 40, the way TEDS is designed, is one mode. If I have a tension and compression load cell, unless I have a modified version of TEDS, I'm only able to program one mode. And the downside with a template 33 or 40 is you're basically, when you send that off to be calibrated, if chances of reprogramming are high, depending on what you want to do and how close you need to make it in. And that might not be cost effective for you. There's special programs that the labs need to have. Some customers, or not customers, some companies lock you out, meaning it's proprietary. And the writing of the chip. So when they lock you out, that effectively means that you sent your equipment to some lab to perform the cal. They're reporting out. You want it to read closer to nominal. You want 10,000 to read 10,000. So now you had an accredited cal. You need to send it back to the company that has the special software. And then since they're not accredited, then probably back to the lab that is accredited if that's the whole scenario. It's, again, a lot of word salad in this. I don't know how many people are using TEDS or not. Template 41 really allows you to use coefficients and do things. And what template 41 effectively does with coefficients is you can quantify those errors and just load them into it and calibrate in millivolts. So a lot of stuff there when you do it. 2-point span, template 40, better comparison that I did. But this 4-point can be 20 points. It can be 127 points. And then if you can get the TED system with the 41, you can use this. So I recommend searching for a template with 41. Do know that compression and tension are different, and that you can only program one mode per TEDS chip. So you're likely going to need 2 TEDS chips or a switch or something if you want to do it. If your bias is concerning, we have 2 meters that just do coefficients. Keep everything together as a system. You don't have to have that separate traceability chain for the meter, for the load cell. Either one of these systems will use coefficients. Our Hattie system with the computer will use coefficients. So lots of choices with indicators. That PSDS will read all the TEDS templates in it. The battery powered one, it's not as good as the other indicators. So really it's a matter of having the discussion. Is my load cell tension compression? Do I need 2 channels? Maybe then TEDS isn't the best solution. And watch out for labs that are just giving you a bunch of data and then they say they program their TEDS chip, because you're going to have chances are you're going to have a large amount of bias. The next thing we move into is like low force stacking weights, off center loading, safety issues. This is common problems that we hear if you're doing those force gauges we talked about earlier, the handhelds, the other ones, low load cells. Most people that I talk to are using some form of weights. I've heard of people like stacking weights, holding a bar, like doing something in tension, having 2 people hold a bar as the thing. There's all kinds of stuff. Normally they buy some weights by Trom. They're a great place to buy weights, buy them from other places. And then they're not corrected for force, which is a huge error, because force is mass times acceleration and assumes the correction for gravity, air density, material density, and some of the other stuff. And when I say stacking weights, this is not uncommon. There's an S-beam loaded flat, and there's my hand. Look at that. And purposely looked at that. As far as watching this thing, you can weights will fall. Getting them centered is a problem. There's a lot of different stuff on there that it needs to be considered when you're doing that. That's why that machine, the PCM is good. We have another machine, BCM machine. The BCM machine will go. Excuse me. The BCM machine will go. I'm trying to click on this. So BCM machine will go to 10,000 pounds. The other machine goes to the PCM goes to 2000. There's more on mass to force. This is in your sheet. You can click on it. It takes you to the blog. Basically, the extremes of gravity from the Earth to the pole, unless you're at a certain longitude and latitude, the extremes are about 0.5% overall error. And this website goes through how you find your gravity, how you can correct it, all of that. It's in the slide deck. You can go to use these tools, use Google Maps to get your longitude and latitude. Now, NOAA, for our foreign visitors, there's different, for people that are not in North America, there are different websites out there for you. NOAA is the North American, typically. They've mapped all of the regions and know, for lack of a better word, they know the gravity pretty darn well. Typically within a couple parts per million, anywhere that NOAA picks. We have, once you know that and you basically get your gravity at your location, you can start using our sheet here if you want it. This is one of the tools that took a bit of time to develop. If I can get it, click on. But anyway, it's easy force to mass tool, and it can convert back from mass to force. Right here's the mass to force tab. This is the force to mass and mass to force. And we wrote a guidance document for HOA. So you're using class F weights, not a big deal. You can use them all day long. You put the gravity in at your location. You say you take a guesstimate on air density. There's local airports and stuff can give you something very close at normal air pressure. Material density, that's not going to make the biggest deal. You can play around with that. You can use different material densities. Say I wanted like uh, other ones, the machinist handbook, some other things in there. You should account for the uncertainty. Of course, now I needed to edit it. That's why I don't like the online version. But you can see there, and this will spit out a lot of your difference. It's taking gravity and it's taking some additional error here. And in this correction, basically the mass is known to 0.01%. Estimated uncertainty for gravity from NOAA, 5 parts per million gravity bias error, and it corrects everything into much closer to force. So at this point, I have mass weights of 250. It's basically saying in New Jersey at the location that I selected, to apply the right force value, I need to apply 249.61. That is all available for you to do some more research and documentation on. I can go on and on about force to mass and different things. And we also have guidance document online. Common other problems, basically I'm doing these force gauges beside the mass to force, or that different centering fixtures. This is a repeat of the pictures, but you have all these adapters, all these holes and everything else because someone didn't standardize. You have alignment issues that you could have, and the right adapters, buying these sets will work pretty well. There's a PCM. This is some of my marketing lingo and stuff, but if you're looking at doing low force and cannot afford dead weight machines, these are really good machines overall. In terms of accuracy, you basically get at uncertainties of about 0.3 to 0.5, depending what you want to do, and that's good enough for most applications. Certainly good enough to do these are 0.1, so you'd be 2 to 3 times better than that. These force gauges, some of them are 0.5%, so over 10 times better. Load cell to load cells, you're about something like that. If you're calibrating the E74 standard, you can do it. It's a little bit more, you're going to have some additional uncertainty with it. So I did ask if somebody's some comments there, some good comments on these. Okay, so before they fully, I have realized that they mostly you are focusing on load cell calibrations. On my case, I calibrate force machines. Okay, yeah, calibrating, it is mostly load cells in this, but there are some takeaways for force machines because you're using the load cells that were calibrated to go calibrate those force machines. So the some of this applies, the E74 stuff, to have the background and knowledge of that should help. But yeah, I'm not talking about a lot of the E4 stuff. Calibrating meters standalone? That's a good question. I like the 8588. Of course, I think I said earlier the Fluke 5800s. If you just want to calibrate the meter standalone, we work with Ohms Labs to make a voltage simulator. I have some stuff online. I'll get at the break. And then somebody said they love their PCM. Love that comment, of course. How important are load cell simulators? Yeah, so when we were talking about the meters, I'm going to hold those questions, Luke and Tim, a little bit. But yeah, if you want to establish that traceability chain, I have some posts on how you calibrate meters and the simulators and how to do that. And then there's whether it's with E7 in accordance with following E74, or we have like an ultra cheap, pretty good simulator that could be used if you just want to play around with some stuff. You can certainly get traceability with it, but if you want to calibrate to the E74 guidelines, it's not good enough for that because it doesn't have the steps. It's like a $500 simulator compared to like one that's 4,000. I don't want to scare people away with pricing, but high precision resistors, if anyone work with Jay Clevens, a brilliant guy at Ohms Labs. So the pleasure of working with him on a joint project to develop some simulators for calibration, and they are much more expensive than just taking some rather good precision resistors, putting on a board and putting a switch on it when you really get to the high end stuff. So we had that. About 31% are calibrating to E74. The standard is the new standard should be out this year. Not much is changing. And it should be an E74-25. Some subtle changes. I'm not too big on most of them. Changing things to elastic force instruments, some word changes specifically to the standard. There's a dumb line in the standard that says for simulators that you shall follow the guidance in the annex, and the annex is non-mandatory, so that's going to be corrected to a should. Very like not too much meat or worthwhile changes are coming. Nothing really to the calculations or anything else. More words, descriptive terms. So even though you're not calibrating to E74 or your company wants to calibrate to E74, there are standards that may come into play that reference E74, ASHTO T22, 68, E4, of course. Probably have some people here that are testing the testing machines, or they're using ISO 7500, but that doesn't reference E74. Though there's things what we're talking about and the errors that we're going to talk about later for that group, that'll be beneficial because the errors on our end on the calibration side certainly apply to the field side, right? Like marking equipment already earlier, how you're using, if you're using any S beams, are you telling the lab how you're calibrating them? If you're pulling out that top adapter, that what I call the integral threaded adapter, it's going to be much different results that are going to put your testing machines out of tolerance, and you'll be adjusting something that's actually good. Uh, yeah, ASC 39, E10 was the Brunel hardness. There's a line in there under the verification about the having to have devices calibrated with a class AA, meaning primary standards, and E18 has that same line. So hardness testers. So if you are doing hardness testers or calibrating to E10 or E18, E74 is going to have some reference. Of course, it have reference to E439 and the other ones. What E74 basically says is a primary standard is this. It's a deadweight force directly applied without mechanism, levers, all the multipliers, and whose mass is determined with reference standards traceable for national standards of mass. It's basically mass, right? We're giving some target mass that we know is going to generate a force, because we're correcting for air density, air gravity, air density, material density, and gravity. And to be classified as primary, they need to be determined within 50 parts per million, and then values, and that's in section 6.1.2. And then if we're going to make a force machine, we want to know where you live, where you're going to make the measurements, more specifically. Um, because if we're going to design a machine and you want a primary standard, you're going to give us all of this information. You're going to have to provide us with this. We will know the density. We will have density coupons, cut of weights. We will have density certs. We will have all that. And then we're going to make the machine and we're going to have it adjusted, trim it in, and it's going to be much better than 50 parts per million. Most of our machines and most of the machines that we provide are better than much better than 20 parts per, or, around 20 parts per million, depending on the size of the machine and the size of the weights. So there's where we were getting into some surface finish, and this is ASME B46.1. But yeah, you can get into different surface finishes, and you can certainly measure them. Like I said, we use different techniques for the surface finish that we find good enough. Secondary force standard is the calibration by which has been established by comparison with primary. So I take this proving ring, I put it in a dead weight machine, it can become a secondary standard. I take this load cell, put it in a dead weight machine, it becomes a secondary standard. This is a very cool machine. It's a lever machine. For this, you're doing some inner comparisons, probably using a load cell and doing some other stuff. Not many people have lever machines. I am a huge fan of them, and why I like them is because you can get to high forces with a lot less weight. That being said, they are finicky, they are expensive. This machine to the right just looks super expensive in general. So a hydraulic amplification I like a little bit more, and I just finished a paper on that and why. But example of some secondary force standards there are UCM. Some people online said they had a PCM, yay for the PCM, super yay for the UCM. We've made this machine since the 1950s, changed it along the way, just slightly. Learned some lessons as far as plumb level square rigid, made it more rigid, added more material to it, automated it recently with an automation upgrade. So if you make a good machine and you automate a good machine, you don't need to really change the design characteristics all that much. There are lessons learned. Of course, the old machines used to have this counterbalance up here. That's gone. Learned a lot of stuff along the way, but they are not night and day. Difference. Uh, Secondary force standard, this ASTM is basically saying, hey, you use primary standards, you can assign this class AA range, and then those class AA standards can use, and you can calibrate class A. And I know this is probably for the people that do not calibrate or learning something. I like this line better, which basically ASTM was written back around sometime in the 30s. It was a combined standard of E4 and E74, and they broke it out, I think, late 30s or 40s. I have some copies in the 40s where it's broken out. Though, if you look at what ASTM is doing, and we'll look at the formulas and some other stuff that it's basically building a pyramid. And if you look at this pyramid, primary standards to secondary, it's basically saying, all right, we're going to build in ratios that are 10 to 1. We want our primaries to be 0.005. By multiplying this lower limit factor by 2000, we're going to guarantee the first point is 0.05. And then the class AA, they have this multiplier that's 400 that I was talking about, which basically says, hey, I'm 5 to 1. And then that end result, when I go out and calibrate that testing machine, unless it's an Instron machine that's a 0.5%, then I'm 4 to 1. And there's ways, if you're doing an Instron machine, if you want to maintain the 4 to 1, you multiply by 800. But that's, your ranges are such that we've inherently built this into the system where I calibrate this load cell following the standard. Hopefully I send it to Morehouse for dead weight or NIST or wherever. I get my cal back, I put it in my machine. I know at least Morehouse gave me they were 10 times better. Then when I do these other cells, I have my class AA, and by the description of the standard multiplying by 2000 whatnot, I know that I'm 5 times better than what I'm going to calibrate for another customer when I multiply their results by 400. And then someone's going to go out and do a materials test machine, and they know that the worst case scenario, if everybody's following the standard, is that whatever numbers they gave me, and if they follow the standard correctly, we are at least 4 times better than what we're calibrating. I am not a fan of test accuracy ratios because you can't scale them, like keep going and going and going. This is very contained. There's 3 steps, right? The testing machine, I'm going to send to some lab that's going to send to another lab, and boom, we're done. We're not going to keep propagating it where I need some number like 1,000 to 1 to keep going, because everywhere needs to be 4 to 1. So the way E74 works and all these numbers that I'm spewing out, I have an old cert that's generated, and I like this because it captures everything. Now we have more stuff on our certs. It's 2 pages instead of to capture all this from all the additional requirements that were added. But what I like most about this is it shows. So someone sends the equipment in, we allow it to come to room temperature. Usually a 24-hour soak is good. If somebody sends us in a 1,000,000-pound load cell that weighs 1,000 pounds, 24 hours is probably not enough to come to room temperature. If somebody sends us in something that weighs 1 pound, 24 hours is probably overkill. So there is that effect on materials. Though a good rule of thumb is about at least the day before. Warm up the instrumentation, that's hook it up to your meter. Select 10 to 11 points. The standard's very descriptive in that you cannot use it below the first calibrated non-zero point. So the reason I say 11 points here is most people out there doing field work, do not like substituting load cells that much, because if you can use 1 load cell instead of using 2, your cycle time and the calibrating the machine is a lot easier than if you're just if you have to change out 2 or 3 load cells. So ASTM works, then you fixture the unit under test, that's UUT, in the test frame, exercise 2 to 4 times. I recommend at least 4 times. The standard says at least 2. I don't like that part. I wish it would change, because you really want that material, if it's been sitting for a while, all those molecules that are inside, you really want to get them going and excited, because if you don't do it, your first run of data is going to be much worse. So an exercise cycle on most load cells of like 4 times is not bad at all. Apply the first series of forces, that's run 1. Apply your second series of forces. This is where you rotate. So the standard says, okay, that second series, we're going to rotate the device 120 degrees. If possible. There's some language in there that if you can, or a proving ring, you rotate at 60 or 300, or positive 60, negative 60. Anyway, so in general, we're going to rotate 120. If it's a compression and tension load cell, now we're going to switch to tension after the second run, do all 3 cycles, 1, 2, 3 runs, rotating in between. And if it's compression only, we'll rotate again. So we have 0 degree orientation, 120 degree orientation, and 240 degree orientation. We're going to get all of this data is what we've got. And we're going to reduce the zeros, because obviously we have beginning and ending zeros. Reduce the zeros, and we're going to take all these zeros and plot everything against each other. Apply as third series, and once we apply that all against each other, what we start using is what's called a polynomial equation, or some call it least squares fit. So those that are calibrating or wanting to calibrate to E74, this is what happens where the mistakes happen, is what they basically do is they take, I'm going to erase this, so bear with me. The standard is not good, and I have petitioned to get this changed, and everybody, the people on the committee, thinks the standard is crystal clear. So what people tend to do is they tend to take this data set that's reduced, and in their Excel file, they'll average it. And then they'll run analysis. The function in Excel, if you want to run it, is linest, linear estimation. And then you say line X, and then you'll have to look at the command set, and then you say something like, I want to do second, third, fourth degree. Anyway, with that, I don't know it off the top of my head, but it's line S function, and they'll plot, and this is what you want to look at, because they'll want to plot these force applied values versus the average of these values. The way the standard is written is not that. The way the standard is written is very descriptive and clear. And I know I'm probably boring the other people, but the way the standard says is basically, the way I want to run my data, instead of averaging all this, I want to treat each set of data separately. So 200, 1000, this is my X and my Y, right? And then I want to redo this 200 to 1000, and this is going to be this is going to be a Y, and this is going to be a Y. So if I was aligning this, and I'm doing this with I do force applied, run one. And then I do all my force applied values. Again, I would type in the exact same values, run 2. And then I would do all my force apply values and run 3. And then I would use this linest function in Excel and plot all of these. I think this is X and this is Y. And I would plot all these against each other. And that is going to give me a set of coefficients. And then those coefficients are used to generate this line. Am I being a pain in the butt saying not to use the average? The average will get you close, but it's not what the standard says. So that's the little bit additional for those doing. That's what I see a lot in E74. And then, so after we've plotted this curve and we've done it correctly, plotting them against each other, we figured out the degree fit, used the annex to select everything. Basically what E74 does is then it says, okay, I'm going to take the deviations from this curve. I'm going to take these values minus the observed values over here, and I'm going to plot the deviation. So that's this piece. And then they root sum square these in this equation. Standard deviation is the square root of the sum of the squares, and n minus m minus 1, where n is the sample size, m is the degree of polynomial fit. And the penalty on this is if I fit to like a third degree here, that my m becomes a 3. That makes my denominator smaller, which gives me a larger number when we calculate this lower limit factor. At the end of all of this, ASTM was written so you multiply this standard deviation that then we convert to whatever unit we're in. We multiply it by 2.4, which gives me this. And I think I jumped the gun earlier. So lots of stuff there. If you're a beginner and following on, I'm going to go on with that. If you're following E74, the blog, there's a webinar on it, and there's some other stuff, and I'm happy to answer questions on it as well. But that's all it does. It's a procedure that takes multiple readings, at least over 30 points, and we get a statistical estimate that plots that curve for us that we know within X. And then we have this multiplication factor 2.4 for 98.2% confidence, and multiply that by 400, 500, and that's it. So E74 is descriptive. That basically says if a force measuring device is to be used to measure forces during decrease, then it must be calibrated in that manner. It says about separate curves should be developed. And then I say E74 mentions nowhere about doing this. This is industry needs something for this. I don't know if it matters to people, but if you use a combined curve, that basically says, hey, I'm going to take a larger estimate of errors, and just so I can make measurements anywhere inside this curve. If I go to capacity and down, if I go only to 80% and down, I know my error. It's better to do separate curves, but the descending curve, the kicker on descending measurements is this, and that is a descending curve is only valid if the device is loaded to full capacity. An ascending curve, generally the way load cells work, they don't care as much if you only go to half capacity, as long as you've exercised it recently, and then there's material properties and all that. But yeah, on the descending curve, they always want you to go capacities to capacity, because each curve you'll get if you only go to half capacity, you'll get a different curve coming down than if you go to full capacity. So an ascending curve can be used, and then I recommend the combine, just because it's how you're going to quantify the error. Just take the higher error sometimes, but you can get different load points. The question earlier, if you have the 10,000 pound load cell, you could get ascending, descending points at 10,000 and 5,000, and have two different sheets and four different curves total, two for ascending, two for descending. Some additional stuff with the standard, it basically says non-zero force point. If we took this number here and multiplied that by 400, we get the first point as 52.8, but the standard says since you just did 200, you can't go that low. And I know people in the field want to go as low as possible, so you basically get to the point where you ask your calibration provider to go as low as they possibly can for you. But then ASTM recommends 2%. ISO 376, it's a shall instead of a recommend. So ISO 376, if anybody's using, that's international standard, you cannot go lower than 2%. So what do we see happening in the field? Here's an example of a cert from one of our competitors. Class A lower limits, 192.3. First force point is 500. That should never happen. This says basically shall not include forces outside the range of calibration, and the first force cannot be less than 400 or 2000 times the resolution. So other things that happen is the class A, double A, you have to follow that pyramid, basically meaning class double A requires primary standards. Class double A doesn't pass on another class double A. And here's an old cert. This company has since corrected it, but I looked at this, and basically they said, hey, I have this gold standard. This is a great load cell, this gold standard, and I'm assigning a class double A. You can never do that. You have to use primary standards, which is dead weights. That's all this is about. I fully think if you're using interface gold standards, great load cells, nothing bad to say about them. So do not assign a class double A range of forces unless you're calibrating with primary standards better than 005. And then do not assign a class A unless you're calibrating a device that has a class double A verified range of forces. Why I would ask people or talk to people about considering the E74 standard, and then I'll get to some of these questions, is basically because it makes uncertainty. It captures that reproducibility element. That expected performance of the device is captured. All that word salad that I just threw out, and I know people are, when you're new to metrology, it's like drinking from a fire hose. I turned the fire hose on, and you're trying to quench your thirst there. And I appreciate those that are still here, appreciate you going through it. And I guarantee you it will click, and that you're new and you dig into this and say, oh, that's what he was saying, or this and that. And it's 100% okay if it doesn't make any sense, because it is so much stuff packed into this this 4.5 hour session. So If you use E74 and you're familiar with JCGM, which is the Guide to Uncertainty Measurement, people call it the gum starts talking about type A, type B. This is not a full uncertainty class. So you have that reproducibility component quantified. Your calibration is done in accordance with a legal documented standard, which is your CYA, right? Or CYB is a better term, so I don't, swear, is cover your butt scenario. I've sent it off, even though I'm not calibrating uh, equipment to class A, double A, whatever that Henry said. I sent it to, and I have an E74 calibration. That makes my life so much easier on the fact that I have this documented legal standard. I have a quantified expected performance of my device in that ASTM lower limit factor, which is a type A uncertainty component. Type A is statistical analysis. Type B is basically other methods. Super bland and super simplified for this discussion. And then I start doing an uncertainty analysis, right? And if I'm going to do this, our guidance is real easy. Take that lower limit factor, take repeatability of do some repeatability studies, do your R&R between technicians, and then I'm going to start doing all this other stuff. 5 R's in the E down here, resolution of the best existing device, reference standard resolution, reference standard uncertainty, reference standard stability, environmental factors, all of this stuff. What we see people mistakenly do is now they go back to that spec sheet. And I would say if you have an E74 cal, these terms are virtually nice to know. They're worthless to you. You'll never use them. You're going to use that curve fit, that what it should read. You're going to use those numbers in the coefficient. So I don't care about SED. I don't care about nonlinearity. I've corrected all that lower limit factor, the statistical estimate of errors, has incorporated. I said, as long as I use that polynomial, I'm good, right? And I need to use a polynomial for descending measurements. Those other things, these numbers are nice to have. They might give you some inclination of how well your device will calibrate T74, but really it's how well it's compensated for different bending moments and effects, because not all equipment is the same. So, and load cells will pick it up. So if you want to do a calibration analysis or start diving into uncertainty, what you need is the report. You need the uncertainty of the reference standard. You absolutely need history, because we want to know what's it changing with one calibration to the next. Multiple years of history. The more years you have, the better. The more it opens up your ability to do different things as far as uncertainty analysis. Manufacturer specification. Now, you can use this for environmental. You can also use it for meaning temperature effect on zero. You can also use it for some side load. I know some people had made some nice comments to me about Morehouse UCMs. The Morehouse UCMs aren't perfect. You're going to get a little bit of side load, and the specification in it, I know, shocking, is such that you can say, I can tell you if you're using one of our cells, the contribution, which is a type B, is next to nothing. And I wish I knew why it was doing that, but it's about 30 parts per million. The worst case side load that I usually instruct people when I coach or help them with the uncertainties, that say, look, the maximum you can be off in our machine is about 3/16 of an inch, or 1/16 of an inch, and that as long as the tie bars aren't touching, and that correlates to this. And then you error sources, and then you guys and gals, technicians or somebody, you have to do all these other requirements if you're accredited. Proficiency test, R&Rs between different technicians, all that other stuff. So here's what that looks like. Quick wrote a paper back in 2017 and said, look, hey, dead weight, we just calibrate something. This is how uncertainty starts to look. I dead weight cals, adjusted, do all this. This is a 120K machine. All the weights were calibrated by NIST. They were adjusted in. NIST is awesome. They they're expensive, but they're well worth it when you get what you pay for on that one. So we calibrate then, if we're looking at E74, we calibrate a load cell, and a customer, then we give that to the customer, those with UCMs or PCMs, you go put that in your machine. We did all these additional tests right here, resolution, converted it to the Fig Newtons, the Newtons, of course, to stay in the UUT repeatability. Repeatability captured between technician, captured stability, captured environmental, captured side load sensitivity. And at the end of everything, we said, okay, what is this? And this is at the 20%. So if the capacity of this were 100,000, we're basically the best we can get under the most ideal conditions is about 0.02% at 20% of the load cell's capacity in a UCM. And then we said, okay, let's use that UCM to calibrate another load cell. And let's see how good we can get. Well, we cheated a little bit. And when I say we cheated a little bit, we basically used the same exact repeatability numbers. You see these? And we did this intentionally, and it's in the paper. And the reason we did it intentionally is to say, this is how uncertainty propagates. This is the absolute best we can get. So we wanted to take away all these variables, like, hey, what if you had a better machine? What if you did this and this? And say, no, let's propagate them like they're the same, and we've just added this additional uncertainty. So the best we could get was about 0.31%, and that means it's going to be a heck of a lot higher than the absolute best theoretical. So tier 2 is a realistic expectation for a UCM, especially if you have automated, to be down there around 0.2. We do a lot of budgets, help a lot of people with it. 0.2 to 0.4, really realistic. You kind of have to invest in some automation and some other stuff to get there. Our uncertainty, and I'm going to go to it, and then we're going to take a break. Our uncertainty, and you say, why did you just skip that slide? Because I'm going right to, I'm going to actually open the budget. I did this, I cannot tell you how many weekends of my life were spent between 2015 probably to about 2017, and then we still go in and make changes. I know one of our engineers is very versed in Excel, so they ended up making some interpolation. I forget what it's called now. It's a mathematical function that makes it even better to make sure the line or the report that we give you that the uncertainty does not exceed what the calculation is, and doing higher end. But yeah, this is not filled out, but everything in here, instructions. I mean, this seems basic, right? B4 on the CMC sheet, laboratory technicians, initials, standards, all of this stuff is explained. And there's the 16th of an inch. If the number on the specification is 0.5%, multiply it by a 16th of an inch, you get 0.03. That's a miscellaneous area. Convert repeatability to engineering. It's set up. There's so many bells and whistles in here. This is R&R between techs. If you're in millivolts, this thing is set up that says, I'm going to convert millivolts to pounds force, or I'm going to convert it to something else. I can convert it uncertainty worksheet. I can work my uncertainties in absolutely anything that I want to do. There's a really crappy, I want to redo this. I have a better one. There's if I want to do a round robin PT test, and these K's should be italicized, but that's in here, like some basic maths in there. But if I want to know how to calculate resolution, the question I was struggling earlier a little bit and not doing it quickly, resolution per count. I have a 10,000 pound load cell that's, yeah, edit copy. It's of course locked. I want to do that. The math is in there for that. Like anything you can think about, but you can go on here, and I'll pull, since we're going to break, and I have this right here, I'll pull I'll pull a budget so you can see what one actually looks like filled out. Load cells 5001. I'll pull. Okay, no, I don't want that one. Of course, I pulled the wrong one. Okay, so here's a filled out budget. This is our £1,000,000 standard. This one is filled out. 6/18/24. That was the cow. Here's our stability. All entered in off of data sets. I have all these. Look, I have years of history from this. You can do cool things with AI too that I would love to have a course on how to use AI and bootstrapping and prediction and confidence intervals and all kinds of fun stuff for you new people that would really be fun. But okay, so I put all this data in. I have some repeatability data. I have some R&R between texts. I would probably get more repeatability, urge anybody to get more repeatability data than what I have on here, because it's easy to do once you have it. But what this does when it's all said and done is I can click each individual point using the Wells Satherthwaite, which the GUM recommends. And I can look in and I can start making assumptions or decisions based on things. At that 30,000 pound test point right here, the percentage of contribution from that ASTM lower limit factor is dominant. 90.48% of my overall budget. If I wanted better, if I wanted to attack anything, I would look into maybe a second range on the load cell. I might look into a different load cell for something lower than 30,000 pounds. But if we look at this E74, if we start going to say 300,000 pounds, E74 is dominant. Look at I go to 700,000 pounds. Look what happened. The stability of my reference is 63.85%. The ASTM E74 lower limit factor is no longer dominant. And for others that are, this can allow you to make a lot of decisions quickly when you populate it and say, I need another cell for another range. Or you can use this with testing machines too. You could just do your repeatability study in the testing machines. Lots of people use it. You might say, all right, I want all my cells to be within 0.2%. I need to pick up a separate range to do customer equipment if they want me to. I need to do this. So there is so much power in understanding this sheet, and there's so much built into it. Like if you have low repeatability, you can convert everything so it equals way beyond this course here. But look at my coverage factor, 95.45% is what we're using on this. If I wanted, I could change that to 95% actually, if I wanted to. But if I go to the summary sheet here, this basically says it's filled out. There's my actual uncertainty and my uncertainty per point. And if I want to give A2LA a nice little formula, I'm probably going to over-report my uncertainty in some of these cases because because I have to fit it. And that's what our one engineer, James, did. And see, when I say he knows Excel beyond me, this is the lambda function. Those guys that are programmers might know this. By row, you can see lambda, sequence, spit it all out. But if I look at, I opened this with saying like, look, we try to maintain 01 or better, and you start looking at this 200 from 200,000 to a million, we're better than 01. We're 02, and this is using a DMP 40. There's different stuff. There's first try. There's what's going on with this math to keep doing these different attempts to maximize this straight line formula. Anyway, that is a lot of info, and I know people are confused. My thought process is we have the guidance documents online. We have lots of them here. We have check them out. make a note, do it now before you forget. You can go online, you can go to MH4, you can go to guidance documents, and you can say, all right, I have a UCM, I have a PCM, I have whatever, and uh, there's guidance on here for calculating a force uncertainty for a cow machine that just basically explains all of this if you want to dig into it. There's a week-long courses on uncertainty and how to do uncertainty and how to understand it, your type A's, type B's. All I can say is, yeah, we've tried to pack the website with as much as possible so people that have that quest for knowledge can go,